Thank you very much. So, hi, I'm Jason Alderman from the San Diego office, and today is part 2 of our machine learning talks. This one is going to be on practical applications. So previously, super fast run through of what we talked about. We talked about how machine learning is a subset of AI that works on specialized domains, that it flips traditional programming on its head, where you just have to feed it in the data and the answers, and then you get the rules, the model out of it. We talked about all the steps that you need to do and how this works, and you are generating models that you tune, and then they can make predictions. There are many different types of ML models. Artificial neural networks are one of them, which we focused on. There's a whole lot of math, a heck ton of math, but all of these are basically nodes inside layers inside a neural network, where each neuron is actually a computer function that is generally a weighted sum of all of the previous nodes in the last layer. And then you can use some fancy math, differential equations called gradients, to figure out which direction you need to go to minimize or maximize the response and get the outputs that you want. And then you can pass those details back up the chain through backpropagation, blah, blah, blah. And we covered a lot. So today, I promise, unfortunately, that there will be a little bit less math. But last time we talked about what machine learning was, how it worked, and a little bit of how we could use it in setting up our own models. Today, we're going to talk about the so what. What is it good for? When should we use it? Why should we care? And so first of all, when we're thinking about what is it good for, it's good to think of how machine learning models work. And remember, they're statistical models. So they're taking a giant mess of numbers, those tensors worth of data, and they're statistically sorting it. This is an image from the Williams College Museum of Art's Collection Explorer, which I had the chance to work on. It's using a visualizer called a Vicus Viewer. And this is taking all of the artworks in the Williams College art collection, because Williams College is a college in the Berkshires that does art history. And they have an extensive art collection and a museum associated with their college, but they've digitized all of the works that are in their collection pretty much, and they've put together some really interesting visualizations around it. And so if you zoom in on this, you can start to see that there are some patterns here where it's grouping things that are similar. And these things might be by the same artist, they might be of similar subjects, they might be on similar media. And when you zoom out again, you can filter these. And so you can have it highlight all of the prints. And then as you roll over different things like screen prints, it shows where those groupings are. And it's basically breaking all of this data up and visualizing it in a way where it's separating similar groups. And this particular visualization is called a t-SNE, which is a t-distributed stochastic neighbor embedding. I'm not going to pretend to understand exactly what all those words mean, but just know that embedding is a kind of representation of something. Like a word embedding is mapping those words to numbers so that you can use that. And t-SNEs don't have to be two-dimensional. T-SNEs can be three-dimensional. This is using the MNIST database of handwriting that was used for the beginning OCR machine learning algorithms. And you can see that it's showing the distributions of how these patterns match up. And so when you feed it a new number, it says, oh, okay, this has properties, it probably belongs over here. But you can see that there are also some false positives in there. You can see a 7 amongst the 4s and things like that. But that's mostly what a lot of these machine learning algorithms are doing. They're doing a lot of math, and they're figuring out statistically which groupings things should belong in. There's some links that will be in the slide deck afterwards so that you can read a whole lot more about t-SNE and about statistical stuff. But before we go on further, a lot of this is data science. There's a whole field devoted to this, and we have a Teams channel called Craft Circle for Data. And if you're interested in this, right now there's not a lot of activity in that channel, but go join the channel and maybe help bring that channel a little bit back to life. So we're talking about how machine learning is really good at statistically sorting things. It's getting in inputs and it's finding a way to turn them into outputs through a lot of mathematical operations. Classifying inputs is probably the number one thing that machine learning is good at. So you can feed it a bunch of images and it can say, this is a cat, this is a dog, this is, you feed it an image of a truck and it's really kind of confused because it's only been trained on animals. So that's one good example of how machine learning can be used practically. There are links in this. Please look up Rick afterwards. He's got a Sitecore library that interfaces with a lot of these image recognition algorithms in the cloud. And this is something that you could use today in your work. A second example of how machine learning is good is in detecting outliers, things that shouldn't be there. Duck, 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 goose, duck. So a common example when people are learning machine learning in a lot of the courses is credit card fraud detection. How does your bank know from all of the data of the location of where you're purchasing something, the amount of what you're purchasing, the store that you're purchasing it from, et cetera? How do they know what's fraud and what's not? It's by doing that statistical analysis, making that kind of mathematical model, and then seeing what are the outliers that are way out that shouldn't be there. Likewise, for medicine, there's been a lot of anomaly detection, everything from looking at biopsy cells or looking for data in blood samples to try to detect cancer and find ways that you can detect diseases early. Another thing that I've heard of is that there are people who have made machine learning algorithms where you can just talk on a phone and it will tell the algorithm will be able to determine if you have the coronavirus before some of these tests might be able to, just by doing modeling of the sound that your lungs are making and finding certain markers and signatures in the ways that you're speaking. Same with some neurodegenerative diseases like Parkinson's. They can tell tiny warbles in your speech that are predictive markers of these diseases early. And so, again, that leads into predictive analysis, predicting outputs. One great example is General Electric makes a lot of motors, jet engines for fleets of aircraft, jet engines that are used in fleets of aircraft around the world. And they use this thing called predictive analytics. They have a tool called Predix, and it looks at all the data that they're streaming from these engines. Every time that the plane lands, it downloads terabytes of data, and they look at all of these numbers about how the engine is performing, and they can say, okay, in about 1 month, this engine is probably going to fail because these other engines had these same kind of signatures and they had similar problems. So we should schedule maintenance next week for this engine and prevent any kind of problems. Additionally, Stash Noga on our team in San Diego was talking to me about an intelligence tool that's used for strategic intelligence, which can look for patterns in socioeconomic patterns that can predict certain events in countries or in economies that can try to prevent certain events from happening from some of his intelligence work. And again, predictive analysis is also in the stock market in trying to make machine learning algorithms that can predict which stocks are going to do well, which stocks aren't. Machine learning is super helpful when it comes to drug discovery. It's been used more and more for optimizing chemical reactions. And you can train these statistical models to look at ways that chemicals go together to create new drugs. As well as if you've used Photoshop, even things like the content-aware fill, where it's able to predict what the pixels would be if an image weren't in the image. So you drag your lasso tool around something, you do content-aware fill, and it fills it in. And it doesn't do the best job, but there are tools that are getting better and better. There's a tool called Facet.ai, which aims to be a Photoshop imbued with a whole lot of AI. And this is what if Photoshop were designed today with all of these machine learning techniques. And it can do things like give you an image and then you click on a certain thing like, or you type I want to highlight the hat, and it will highlight just the hat. Or you can click on the hat and it knows what a hat is, so it draws the lasso around it. Or it crops out the background completely. Or it can recolor images, which is something that your clients might have to do a lot with a lot of their product imagery. And it can create multiple color variations of something, and you can just say, I want this one, this one, this one, this one. I want the person pink, yellow, and green. Good to go. There's a tool called deepcode.ai, which if you're a programmer and you're using Visual Studio, this is something that does static code analysis on your code as you're typing it wicked fast. And it can tell you, you're going to have a problem in your code in these parts because of this. And it gives you an English sentence that explains what you might need to do because there's a security flaw in the way that you're typing the code. And it helps you prevent making mistakes in your code before you make them. And so we've talked about classifying, detecting outliers, and predicting potential futures with this. Another example of what machine learning is good for is mapping inputs to something else. So taking fuzzy inputs and then spitting something out. What we've used this a lot for in our innovation work is we've been using these libraries from Google called the media pipe libraries, and they will take things, as you can see, Eric Parr here on the left is holding his hand up in front of the screen and making gestures, and it is taking that stream of images from the video and it is making a 3D model of his hand skeleton. And so it's taking those still images and creating a 3D model from that based on inferences that it's making from all of the training that it's done at looking at so many different hand gestures. And MediaPipe has a lot of different libraries that are like this. Everything from face detection to drawing a mesh of points around a face to doing skeleton tracking on things. There's a tool called crisp.ai, which will take it does what Photoshop did with that content-aware fill and does it for your audio on your calls. So it will basically mute out anything like dogs barking or garbage trucks going by in the background or the clacking of your keyboard. It's pretty impressive stuff. And then Jeremy sent out a link right after the last talk on something that he had run across of tensor holography, where instead of trying to get a computer to calculate all of these intense physics calculations to figure out what the depth of field was for holograms, that scientists had figured out a way to train a machine learning model, and they fed it a whole bunch of inputs of like, here's the source data with the depth data and the color and everything like that, and then what we're looking for is the phase data of a hologram. And the machine learning algorithm essentially taught itself the laws of physics and is able to do that in a much smaller memory footprint and do that really, really quickly. And so now it's possible to do the calculations on a smartphone that used to take a supercomputer to do to generate holograms, because it's just basically one big model. It's basically one big lookup table. And so this is all really exciting stuff, and it leads into another technique of what machine learning is good for. Who here remembers puppy slugs? Okay, so bear with me, there's this thing called Deep Dream from Google, where some scientists were looking at these neural networks, and they decided to flip the neural network. So instead of feeding it in all of the pixels of an image and getting out rock, paper, scissors, they'd feed it in rock, paper, scissors and try to reverse engineer that to create the pixels of an image and create an image. And by doing that, they ended up creating these weird images, where the one on the left is one from Duncan Nichols, where it was his half-eaten donut, and he fed it through this algorithm, and the algorithm is looking at it, it's doing all of those convolutions and pooling, and it's trying to accentuate what it sees in there. And this example Deep Dream algorithm was trained on 120 models of dogs, and so it's trying to find dog faces everywhere. And what it creates are these really bizarre, surreal images. And it's as if the algorithm in the middle of all that convolution and pooling, when it was creating new versions of the image to try to identify the features and find where there might be a dog in this, it's like, do I see a dog here? Do I see a dog here? Do I see a dog here? It's frozen, and we're looking at the image that it's created. And this is, again, why would they do this in the first place? This all sprang from something called generative adversarial networks. There's a great explainer from NVIDIA on this, but the idea was we have to create all this training data for our neural networks. What if we train a neural network to generate the training data and see if it can fool the other one? And a side effect of this was that we found out that we can generate new media. We can basically remix things. And so that's how you get things like style transfer, where you feed in a photo to a neural network that has been trained on hundreds of Van Gogh images or hundreds of Cubist images, and it's going to be able to apply a lot of those features by kind of accentuating that in the original image. And Tillman Bartels sent me, I hope I pronounced your name right, sent me a whole bunch of great links that will be in this presentation afterward. But Artbreeder is a great site where you can test out some of this yourself and play with machine learning networks for generating images. There's also the ability, this is a little bit creepy, to generate a lot of things that don't exist. This X does not exist as kind of a clearinghouse of a lot of these methods where this person that you're seeing on here is not a real person. It's something that is dreamed up by an AI that has looked at lots and lots of images of people and has kind of smushed together a bunch of facial features to create a photograph that at first looks really impressively like a person. But when you look down at the details, sometimes you can see some JPEG artifacts, hair and ears and things like that look a little bit weird. But then also the middle ones are fake listings of houses. All of those images are generated. They fed in a whole bunch of Craigslist listings of sublets, and what they got out was these images. And you can see there's some strange artifacts in the windows. There's some bizarre things with the trees, but at a glance, this looks really real. Likewise, the cat is fake. Music generation. There's Google has a whole project called Magenta with a lot of different demos of things where they've created some neural network models that you can use in really exciting ways to generate music or to play alongside you, where you can feed it a little bit of information and it'll work. They even created this bit of hardware here which lets you create musical instruments that have never been created before or never been heard before, where it's like, what would a flute crossed with a saxophone sound like? And sure enough, it can blend those two sounds together and make an instrument that you can use that might be completely novel. There's also music generation where you can feed a whole bunch of samples of music to an algorithm and have it generate out music. Robin Sloan is a science fiction author who's done some dabbling with machine learning himself, whether by trying to create the music of a fictional country that he wrote about in his book Sourdough. He fed a bunch of Croatian folk music to this algorithm, and it generated out music that the words were kind of a gibberish that didn't make sense but sounded vaguely Eastern European. And it created this really interesting soundtrack for the audiobook of the book Sourdough that he wrote. Text generation, I didn't get a chance to finish this slide with all the examples that I wanted to, but you've probably seen Janelle Shane's work. She does weird things with AI, like generating lists of Halloween costumes or lists of wrestler names and things like that. Really, really fun and interesting and wild stuff where the machine learning algorithm is being fed in a lot of things, remixing them, and kind of giving the spark of creativity for things that you can build from that. There was a sci-fi movie script that was generated early on that was really bad, and they filmed it with Thomas Middleditch. None of the dialogue makes any sense, and it just is like being on acid, I would imagine. But more down to earth, there are algorithms that are taking events like sports events, games, and being able to take the events of what happened, like what timestamp that a shot on goal took, and then turn that into a written article that can be sent out on the journalist, on the news wires. And a quick note really quickly on that text generation stuff is that you might hear a lot about GPT-3, the generative pre-trained transformer, the 3rd edition. And this is from a research institute called OpenAI. GPT-3 is really powerful, and it can generate things that sound a lot like natural text. And the reason is because it has been trained on, I'm exaggerating here, but the entire internet worth of text. And so a lot of people imbue all of this meaning into it, like, wow, it really understands language. It's really putting all these things together really well. But the thing is that it is just remixing content that's out there. And so when you ask it specific things about specific people, for example, the people who have looked at it and analyzed it have found that it is sampling from like bits of sentences from their homepage and bits of sentences from their Wikipedia article, et cetera, and mashing these things up into sentences that make sense because it's been trained on all of this data. But really, it's kind of like it's kind of like how the human brain works when it comes to creativity. It's mashing up a lot of things. And if it's really good at it, you can't notice where the sources are from. But if it's something where it's a kind of a niche domain, you might notice the sources and they might seem fewer. One last example that I wanted to use here is something that's really exciting in the world of VR and computer graphics, which is NVIDIA has something called deep learning. I can't remember what the SS means, but it's basically doing smart scaling on an image. And so it's able to up the frame rate and the detail in an image on the fly using a machine learning algorithm so that a lot of VR applications and 3D heavy applications can run on medium to lower end hardware. And this is going to probably be really useful in the world of VR because we can use this machine learning algorithm to scale up images and make them seem really, really highly detailed on hardware that doesn't have the horsepower to render that kind of stuff. So these were the 5 examples of what machine learning is good for, the 5 general categories. These are just my categories. They might not be that great. In fact, you'll notice that there's a lot of similarity between the top 3 and the bottom 2. So let's just simplify it and say that machine learning is really good at classifying and really good at remixing. And we'll leave it at that. So now that we know what machine learning is good for, when should we use it? And to answer this question, what is a machine bad at? And conversely, what are you, who are not a machine, good at? Well, we're really good at recognizing patterns, just like these machines are. But we also understand the context of this. I may have mentioned this in my last talk, but if you're on Twitter and you are joking with a friend and your friend says, I'm going to put pineapple on your pizza, and you respond by saying, I will kill you, Twitter and their machine learning algorithms that are fighting abuse might block you and say you're suspended for threatening to kill somebody. Because Twitter and their machine learning algorithms don't understand the context that you were saying that in. That like, I'll kill you, man, is different from I will kill you. So understanding context is something that humans are really good at in that nuance, but machines aren't. And Josh Lovejoy is a senior AI researcher at Microsoft now, used to work at Google. He has a great article, When Are We Going to Start Designing AI with Purpose? And one of the things he does is break down the things that are uniquely human and uniquely AI. Because what you want to do is use machine learning, and again, I'm using machine learning and AI a little bit interchangeably here, but I mean machine learning. Use machine learning for the things that machines are good at, and then save the things that humans are good at, save the things for humans that humans are good at. Tom and Limoncelli had an article in the Association for Computing Machinery called Automation Should Be Like Iron Man, Not Like Ultron. And he said that what we want is something that is more like Jarvis and like Iron Man's suit. Tony Stark can do all of these calculations on speed and thrust and propulsion and projectiles himself, but it's nice that he has a computer that's helping him do all of that heavy math and that heavy lifting. But when it comes down to it, he's the one who's steering. He's the one who has agency. He's the one who's making the decisions. Whereas when you have a machine that is like Ultron, this invention of Iron Man, if you've seen the Avengers films or read the comics, Ultron is autonomous. Ultron is making all of the calls. And when it comes to debugging, like why is this machine trying to run amok and take over the world, it's really hard to figure that out because it's a really, really complicated system inside the neural network of that brain. So it's better to have machine learning do things that are heavy lifting for us, but not try to do everything. And machine learning, when it comes down to creating an interface for getting that person involved, poses a user experience challenge. When I worked at a small machine learning startup, we like to break this thing down into three kind of principles. First was complexity. You're dealing with really, really complex information, and a lot of the information that you're displaying, you want to be able to show it to the user in a way that makes sense without you don't want to water it down. You don't want to oversimplify it. And you also need to build trust in the decisions that the algorithm is making by providing visualization into this complexity when you're working in a world that is just statistical probabilities. The machine learning algorithm can predict, like, I think that this is 80% cat, but it could be 20% dog. And that's where it's kind of nice for a human to be able to step in. And that's the last part, which is agency. You want a person to have agency. You want a person to be involved. But to do that, you need to give them meaningful criteria so that they can make the decisions. You need that human in the loop. And if this is not, what we came up with is not wholly original. This is something that you will see again and again in a lot of things. And everybody's coming up with their own names for this. Josh Lovejoy at Microsoft, his paper talks about accuracy, learnability, capability, and that roughly maps to the same thing. Learnability, he's talking about building trust with the system. Capability, how do people know what they're able to do with it when you're in, and accuracy is how do they know what they're going to get when it's statistically uncertain. So all that to say, ultimately, you want to do what the late, great Studio Berg described as BASAP. You want to be as smart as a puppy. That was one of their internal slogans. This is from a presentation by Matt Jones, who's now a principal designer at Google AI. And it was borrowed from a phrase by AI scientist Rodney Brooks, who said, we'll be lucky if we can be as smart as a puppy. And the reason for this, why do you want to be as smart as a puppy? Why do you want to BASAP? Is because puppies don't try to do everything for you. And they're really cute and they're really forgivable. And they're like, here, I'm helping. Hi, I just fetched this newspaper. Hi, can I be your friend? And that is the level that you want from an AI, although maybe a little bit less annoying than a very, very hyperactive Chihuahua. So use AI and machine learning for heavy lifting on things that would take you a long time. Let machine learning be that doggo. Finally, so what? Why should we care? You've talked for all this time about machine learning. I'm getting sick of it, Jason. Let's move on. Well, machine learning is everywhere now. It is being used more and more, and it's not always clear how the algorithms work. The Stanford University has a human-centered artificial intelligence group, HAI, and Matt sent me a link to their artificial intelligence index report, which is studying how machine learning is being used. And it shows that 2020 was a banner year for companies investing in AI and for PhDs graduating with degrees and work that had involvement in artificial intelligence and machine learning algorithms. And a lot of those PhDs are not staying in academia, they're going to industry. So a lot of the industries that we're working with are investing more and more and more each year, year after year, in artificial intelligence. So keeping in mind all of these principles and understanding machine learning can help our clients. And we need to understand how machine learning can do that so that we can help their business. But on top of this, and this is something that I really wanted to touch on here and kind of shoehorned in, there are a lot of potential ethical issues with machine learning algorithms. And a great summary of a lot of these issues was a paper that was never published. Timnit Gebru was the head of Google's ethics in AI branch. And I'll talk more about her in a moment. But she put together a paper that was very critical of Google, that talked about a lot of these machine learning algorithms and why there are problems with them. First of all, there's the cost issue. Machine learning algorithms, to train them, take a tremendous amount of money. And so only big companies like Google and Microsoft and Facebook can have the amount of resources to create giant models like this. And unfortunately, they often do it on the backs of unpaid or very cheaply paid labor. So a lot of these algorithms that are machine learning started out with people manually tagging and creating that structured data to train the algorithms. So this is everything from people on Mechanical Turk, which is Amazon's service where you can pay pennies to a person to do tagging on data. That's used, Mechanical Turk is used a lot for training machine learning algorithms. Also, Facebook has tons of people around the world who are flagging content that is potentially damaging and abusive. And that's having a mental health toll on a lot of marginalized communities and people who don't have the resources to choose a different job. So you've got the cost issue on top of a lot of marginalized communities. You've also got the sustainability issue. These machine learning algorithms, to train them is taking a whole lot of energy. And talking about energy, we're talking about NFT and cryptocurrency. I believe next week we'll get into that some more. But the sustainability of these algorithms is potentially impacting climate change in ways that are going to disproportionately affect a lot of marginalized communities in countries that don't have these resources. On top of these, there are a lot of systemic biases, and I'll get to those with a few resources a little bit later. But there are cases where a lot of these algorithms are trained on white people in the Bay Area, and so when they see skin tones that don't match that, they don't know what to do. Thankfully, a lot of these biases for vision AIs are being solved, but there are also a lot of biases in other cases where people are feeding it data that is already biased, and they're getting out outcomes that are therefore biased. Everything from like judge sentencing recommendations to things that affect whether or not you can get a home loan. And then on top of this, Timnit suggested that we are spending all of this effort going in the wrong direction. We're building these models that are really good at remixing things without having a fundamental understanding of the data underlying it. It's like, I get this input, I spit it out to an output, but I don't really understand why I'm doing that. And this can create things that look like they're authentic, the illusory meaning. They can look like they're authentic. Like there's a college student who generated a self-help blog, and it would generate all these fake self-help blog posts and put that out on the internet. And that can potentially be a problem because it could make people think that this is actually real advice because they found it on Google. There's a lot of things with deep fakes that I wanted to get into in this talk that I didn't have time to, but we can talk about that in the questions and answers afterwards, where we're kind of wondering what is true and what is not. And it can be frustrating. But on top of this, what happened right after Timnit Gebru put together this paper, submitted it to a conference talk, was that she was forced out of Google. And it's really been a whole kerfuffle. I highly recommend that you look up some of the news on it. It doesn't look good on Google. Google claims that she didn't follow protocols in submitting the paper to the academic conference, and that it didn't get properly reviewed, and they told her not to publish it. And she said, well, I would like a little bit more transparency into your review process. If this is something like, you need to give my department, which is supposed to be an ethical watchdog department, guidance, you need to give us more guidance on how we are doing things improperly, because as I see it, I'm doing my job. And if we can't reach some agreement, then maybe I need to seek employment elsewhere. And within a week, she had gotten an email to the whole company that said, we've accepted Timnit Gebru's resignation. And so huge kind of firestorm that's going on over there, and it's still a little bit ongoing, but a lot of podcasts and interesting articles on that, so highly recommend you look at it. I said that I'd mention some resources. These books, which will all be linked in the slides. Coded Bias is a documentary about bias that's built into algorithms that is coming to Netflix, but it's free streaming on PBS right now. Algorithms of Oppression and Weapons of Math Destruction, great titles, are really highly critically regarded books on how these algorithms are disproportionately reinforcing inequality in a lot of countries. And Future Ethics by Kenneth Bowles is a Welsh designer, has a lot of really good actionable information on how we can use these future technologies with ethical purposes. So highly recommend that people who are watching this talk go check these books out. And as you're dealing with all of this data, as people, your clients are looking to implement machine learning algorithms and try to amass data themselves, ask them and ask yourselves, does your client really need all of that data? And if they do, can you use techniques like differential privacy, which is a machine learning technique that can kind of scramble things around to make it harder to trace back data and metadata to the individual users? Again, links will be in this slide deck. I'm going to skip over that. And machine learning algorithms are getting even better day by day. There's a team out of MIT that just a few months ago announced that they had figured out a way to replace those algorithms, those functions that are each node in a neural network with a different kind of differential equation. And that made the machine learning system, quote unquote, liquid, where it would adapt to changing conditions and kind of restructure itself on the fly, something that I don't completely understand yet, but it's worth keeping track of because it's always good to be aware of what's possible out there. Machine learning and AI techniques are not going away. And so, we're at the end of this. What are our takeaways? What did we learn? Well, machine learning is good at classifying inputs, detecting and predicting things, mapping and creative remixing. It's especially useful in automation, but it should be used in cases where it's doing things that are hard for people, not the things that might be easy for people. Your machine learning algorithms and machine learning usage should try to be as smart as a puppy, try to make recommendations, try not to do things for people that they don't want done. And be conscious of bias and ethics issues. This is a whole wormhole that you can go down. But that's all I have, and I'll take any questions that you might have now.